Hello again, it's me, Professor Albert, here with Lesson 8. Let's learn some econ. So, last time we talked about how to solve Cobbs-Douglas, and today we just want to look at how to solve all the other different functional forms that are not quite as easy. In short, since we don't have interior solutions, we're just going to want to be able to know what the rules of thumb are for how to quickly solve things like complements and substitutes. So, first, let's look at a perfect complements problem. We'll take generic utility form of u equals the min of q1 and q2. Let y equal 10, i.e. you have $10 to spend, and let the price of good 1 be equal to the price of good 2 be equal to $1. Take a moment, write your Lagrange function, and see if you can find your first order conditions. Well, writing the Lagrange function is easy enough. Let your L equal the min q1, q2, add a lambda, do 10 minus q1 minus q2. But then we're going to need the first order conditions, namely dl dq1, dl dq2, and dl d lambda. Find for me dl dq1. Well, you might have noticed that we've run into a bit of a problem. Namely, the min function is not differentiable. So we know, therefore, that proceeding via the Lagrange method is not going to be very productive. So let's instead have a think. And let's draw it. See if you can remember how to draw perfect complements, and see if you can draw with the appropriate budget, namely P1, P2 equals 1, and you got $10. Hopefully what you came up with looked like this. So let's think this one through. Looking at our graph, what must be true at our optimal point? I.e., where will we be consuming? Well, let's try some points. First off, how many utils do I get if I consume here? Hopefully you note that if I'm on the origin, my Q1 is 0, therefore my utility is 0. Same thing if you consume here. Note, also, if you consume any point like this, we can improve our utility while still staying on our budget. Where's a point that costs the same amount as this that gives me higher utils? Well, you can move down and to the right till you're here. This point is associated with some slightly higher utility curve. Same with this point. Same with this point. Where will this iterative increase of my util while retaining budget stop? Well, it should be clear at this point that our optimal bundles are going to be at the vertices of these big L's. So that tells us how we're going to solve complements. Suppose for a minute that you've got some Q1 and some Q2 that spend your entire budget. And also suppose that you have some Q1 that's greater than your Q2. Well, if this is the case, you have any bundle where your Q1 is greater than your Q2, we know you can increase your utility by decreasing your Q1 slightly and increasing your Q2 slightly. The same thing is going to be in reverse. If you have some Q2 greater than Q1, well, you need to increase your Q1, decrease your Q2. Therefore, if our utility function is given by min of Q1 and Q2, at the max, we must have it be such that Q1 equals Q2. So that gives us two equations, two unknowns. At optimal, we know that Q1 equals Q2, and also our budget tells us it must be that Q1 plus Q2 equals 10. Plugging Q1 equals Q2 into the budget equation, we'd find that 2Q1 equals 2Q2 equals 10. That is, Q1 equals Q2 equals 5. Pretty simple. So let's try a slightly harder one. Here, let's let our utility be given by min of 2 times Q1, comma 3 times Q2, and let our budget be 20 equals Y, P1 equals 3, P2 equals 4. Given this, what's our optimal Q1 and Q2? Think it through. Well, you'll note here that your Q1 and your Q2 are not desired at the same ratio. That is, optimally, we're going to find these vertices at points such that 2Q1 equals 3Q2. That's our first equation. Our second equation, as before, is just going to be the budget constraint. Namely, we know that 3 times Q1 plus 4 times Q2 must be equal to our budget of 20. So we have 2Q1 equals 3Q2, and 3Q1 plus 4Q2 equals 20. Two equations and two unknowns. If you work it out, you'll find that Q2 equals 20 over 8.5, and Q1 equals that times 2/3. Let's do another. Here we have perfect substitutes. I have the most basic form possible. We have our utility given by Q1 plus Q2, and let the price of good 1 and good 2 both be equal to 1, and let your total dollars in your pocket be 10. Given this, what's the correct Lagrange function? Give it a think. Hopefully you came up with L equals Q1 plus Q2 plus lambda times 10 minus Q1 minus Q2. What next? Well, you're going to want your first order conditions. Note that your derivative of L with respect to 1, with good 1, is just going to be 1 minus lambda equals 0. Your differential Lagrange function with respect to good 2 is just going to be 1 minus lambda equals 0. And your third first order condition will just be, again, our budget constraint, namely 10 equals Q1 plus Q2. What do we note from our first two FOCs? Well, we know that lambda equals 1 and lambda equals 1. If we combine these two, we'll note that lambda equals lambda, or 1 equals 1. If we plug these into our budget constraint, we'll note we don't get very much. Well, why is that? Because our first two FOCs are redundant. They both are just saying that the Lagrange multiplier is equal to 1, and that's it. We don't have any additional conditions. When we have three equations and we have two equations and three unknowns, namely lambda equals 1 and this, we cannot solve for all three parts. Well, this tells us that our third first order condition is all we need to obey. As long as we spend such that Q1 plus Q2 equals 10, we will maximize this Lagrange function. But this isn't the only way substitutes can go. Let's see another one. This time, let everything be the same, but let good 2 be priced at P2 equals 2. Again, what's your Lagrange function and what's your FOCs? Give it a think. So starting off here, we note that Lagrange function equals Q1 plus Q2 plus lambda times Q1 plus 2Q2 minus 10. Our first FOC is going to be L1 equals 1 plus lambda equals 0. Our second FOC is going to be 1 plus 2 lambda equals 0. And our third FOC, as always, is just going to be the budget constraint, namely Q1 plus 2Q2 equals 10. So let's think about what these two conditions mean. Well, the first one says that lambda equals negative 1. The second one tells us that lambda equals negative 1/2. What values for lambda let this be true? Well, hopefully you note that that isn't possible. Lambda cannot be equal to both negative 1 and negative 1/2. That will never be the case. So this tells us the Lagrange method has not helped us. So let's go back to our graph of perfect substitutes and see exactly how these two things have happened. Either we have an uninformative first set of FOCs, or we have ones that are completely impossible to meet. So what actually has happened here is we have our budget condition given in a solid black line, and we have our indifference curves given in purple. Either we have it such that they are of exactly the same slope, like we have here, or they're of two different slopes. You'll note because our indifference curves are constantly sloped, either our budget line, which is also constantly sloped, has the same slope, or it does not. Right before we had curvy lines, this line has different slopes all the way along it. So it could be equal in slope to the budget line here, but not equal to it here, 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 here. Again, since perfect substitutes have constant slopes, they either always match or they never match. So what should we do in each case? Well, if our budget is the same slope as our indifference curve, we're going to be maximizing at any point along this line. We don't care whether we drink, in this case, Coke or Pepsi. However, if our budget curve has a different slope than our indifference curves, it's pretty clear which we should consume. Do I get higher utility from consuming Coke or from consuming Pepsi? Looks to me like I should consume the Coke because it puts me at a higher indifference curve. So, in our second case we just did, clearly good 1 was the better deal. It gives us the same amount of utils, namely 1 per unit, and costs half as much. So if Coke is $1 a can and Pepsi $2 a can, you don't care what you consume, which will you buy? The cheaper one. So in general, the fastest way to solve for substitutes is going to be as follows. Determine for each good your marginal utilities per dollar, that is, divide mu1 over p1 and mu2 over p2, and then spend your whole budget on whichever good is the better bang for your buck. And in the rare case where you have the same mu over p for both good 1s and good 2, well, in that case it doesn't matter. Just spend your budget and good to go. So let's do one. Let your utility be given by q1 plus q2. Let p1 be 1 and p2 be 2. And your y is equal to 10. What is your mu over p for both goods? Go find it. Well, you'll note that mu1 is just 1. And p1 is 1. So mu1 over p1 equals 1. Same for good 2. mu2 over p2 equals 1 over 1 equals 1. So which good gives you more utilities per dollar? They're the same. Since they're the same, does it matter which good you buy? No. Doesn't matter at all. Just buy whichever good you want, or some mixture of the two. As long as you spent $10 total and have gotten 10 units total, you have solved this problem. However, if we go into a problem like the second one, let's let the price of good 2 be 2. Which good gives me the higher marginal utility per dollar here? Math it out. Hopefully it went a little like this. mu1 over p1 equals 1 over 1. mu2 over p2 equals 1 over 2. What's better? 1 or a half? Hopefully you note that 1 is greater than a half, so good 1's the better buy. Just spend your whole budget on good 1, i.e. get 10 units of good 1 and 0 of good 2. So this tells us why we shouldn't just blindly set up a Lagrange function and do some derivatives. Some utility functions are not differentiable. That is, if you try to take derivatives of a utility that has the min function in it, like perfect complements, you're going to be in for a world of hurt. It's not going to work and you're going to waste a lot of time. Other utility functions always have corner solutions, or they have solutions where it doesn't matter what you consume. That is, if you have perfect substitutes where you have two quantities and they are added linearly, possibly with coefficients a and b, well, in that case, Lagrangian will work, but you're likely to get uninformative or contradictory first order conditions. So when you encounter things that are not differentiable or not concave or cross the axes, it's fine to set up the Lagrange function, but you should note that you're most likely going to be applying rules of thumb. So for now on, when you encounter a utility function you don't immediately recognize, first check for red flags and determine if there's an interior solution. If there is, go ahead, apply the Lagrange method, and find the interior solution. However, if you've come across special cases, like complements or substitutes, just apply the tools we just learned. If you have complements, find the optimal ratio, plug it into your budget, and then find an appropriate bundle. If you have substitutes, find which goods gives you better bang for your buck, and just buy all of that. And if you're in one of the rare cases where it doesn't matter if you've got good 1 or good 2, well, congrats. There's infinite solutions, pick one. So, this leaves us time for a cadet practice. For each of the ones below, tell me whether we should be looking for a tangency, i.e. if there will be an internal solution that we can find using the Lagrange method in calculus. Give me why or why not. You should do this referencing our red flags we've said before. Next, after looking for a red flag, tell me what the optimal quantities of Q1 and Q2 are. Your utility functions are given by Q1, Q2 equals Q1 plus 2Q2 in exercise A. And in exercise B, we've got min of Q1 and 2Q2. Give it a shot. Let me know how it goes. That's all we have the time for.